use the complex number. Today, I'm just a very quick review what we talked about it last time before continue to the next topic. Uh, as we talked last time, that you said that usually we either write the complex number in form of the rectangular form, like here, so it's x plus j y, or we can write it again like that. So x is the z cosine theta plus j z sine theta, j sine theta. Or here the z is going to z with the magnitude of the z and the angle of theta, which is going to be the polar format, or this one is going to be the exponential format. So all of them are the same thing. So just write the same, um, uh, I would say the complex number in different forms. Basically, these are these four forms that we can write them. And to convert them, we said that the magnitude of the z is just uh, x squared plus y squared, square root of that. And the theta is tangent inverse of y over x, or the same x is z cosine theta, or y is z sine theta that we have. Uh, So these are the one that particular these ones. I expect you to remember them and work with them, um, uh, because we use them a lot throughout this chapter and some part of the next chapter. These are very important things that we need to know that. Um, Well, one other thing I want to mention that the J, that if you look at these, if I plot them in this format, usually if you remember this plot, it's going to be helpful for you to understand what's happening here. So if I have two axes that I'm going to put the real part of the complex number on the horizontal axis and the imaginary part on the vertical axis, um, this is what I'm going to get. So it's going to be X, which is going to be the horizontal part, and the y-axis is going to be the imaginary part. So assume I have the um, complex number showed as a vector with the length of z and angle of theta. So these are what we see here. So you can come here and see them. Remember that the j value, j is the square root of -1, and usually it's shown with I in for mathematics or other fields, but because in circuit we use I for the current, so we use the J. And the important thing is that remember the J square. J square is going to be -1. These three formula that we will face a lot throughout our calculations is that z with the angle of 0. So if you see the theta becomes 0, means that we are on the real axis. And basically what we have, the z with the angle of 0 is just the z, the magnitude of the z. Is like that we have the vector on this axis. Z with the angle of 90 means that we have the vector right on the imaginary part upward. So it's going to be just j times magnitude of the z. And z with the angle of -90 means that we have this z as a vector going downward here. So it's going to be negative jz. Just remember that or memorize these three, particularly because throughout the calculation we use these three a lot as well. And also, if I have the z1 with the magnitude of z1 and angle of theta 1, and z2 with the magnitude of z2 and angle of theta 2, then what I would have if I multiply them, so I would say, so if I multiply them, basically I multiply their magnitude, z1 and z2, and add the angle. If I divide them, I divide the magnitude and subtract the angle. So also these two, we use them a lot. So I discussed these in detail last time. So this is a very quick overview of what they are. So just remember them when we are working in rest of these chapters, particularly when we are dealing with the AC um, signals. Um, Next topic I want to talk about them is going to be the phasors, and again, it's going to be some before we can start to work with AC current. This is another topic that we need to cover. So far we talked about the sinusoidal signal first. Then we talk about complex number. Now we talk about the phasors, and after we talk about the phasors, um, slowly we can start to look into actually the AC current or AC voltage and see how we can work with them. In simple, if that is that if I have um, uh, assume the voltage as a function of t is going to be, we know as a cosine wave, is going to be V max cosine omega t plus theta. If we have that, as if we write uh, any signal we have in this form, so it's a cosine wave, then we call the phasor, and we'll see later on what it is. We call the phasor of that, if this is a V, call the phasor of that is V max with the angle of theta. So if I go back into that complex number, this is very similar like that. So look at it here. It is the polar way of writing the complex number. So this is how we are gonna deal with it. So if we have the sine, or I mean the sinusoidal wave, like the cosine wave is written like that, then we say that the phasor of that cosine wave is the Vmax, which is basically this peak here, the maximum value here, or which is also the amplitude, and the angle of theta, the phase that the theta that we have here. So this is how uh, we do that. Similarly, if we have it as a sine, for example, if I say that I have the, assume I have V2t is going to be V2 max sine um, so omega t plus theta 2. So again, assume another, I have another wave, but it's written as form of the sine. And remember, when it's written form of sine, to convert it to the cosine, I just can come here and subtract 90 degrees from that. So I can write this as V2 max and convert it to cosine. So I have the omega t plus theta 2 minus 90. Now that it's converted to cosine, I can say the phasor of that V2. I can write it as a phasor, so it's going to be its magnitude, the peak magnitude here. So it's going to be V2 max, the maximum of that, the peak of that, and the angle of theta 2 minus 90. So basically remove the omega t, and whatever left is going to be there. So even if we have it as a sine, we can still write it as a phasor just by remove the as I said, the theta, but subtract 90 degrees out of that. We can do the very same thing if we have the, so these are, for example, for voltage. You can do the very same thing if you have the current. So if you have, for example, the IT, let's put it this way. So if I have the IT is going to be, for example, the I max cosine omega t plus theta, then in a phasor format, the I is going to be the I max angle of theta. Similarly, if I have another ones, assume the I2 as a function of t's, I2 max sine omega t plus theta 2. If it is written as a sine, again, simply just convert it to the cosine first. So it's going to be cosine, so the max, so it's going to be cosine omega t plus theta 2 minus 90, and then convert it to the phasor. So it's going to be the I2 is going to be I2 max, and with the angle of similar to what we have for the V is going to be theta 2 minus 90. So either we have in the voltage or current, simply we convert them to the phasor. And as you could look at the phasor is a form of like the complex number. So basically we convert this signal, which is in the time domain and they are function of time, we convert them to some I would say complex number. And we'll see that when we want to do lots of the calculation, it's usually it's going to be like that. So we have whatever we have in the time domain, we convert them to the phasor, we do the calculation in the complex domain, and then we transform them back into time domain. So in general, when we are doing some of the calculation, this is general way of we'll do all the calculation in this chapter. So when we have the, for example, the, let's say, if I have AC AC current or voltage, which is gonna be in form of sinusoidal way. So, for example, we have something like that. So Vt is gonna be V max cosine omega t plus theta, something like that. To do that, we convert them, we basically transform them to phasors. So we are gonna transform current or for example, or voltage to phasor, such as for example this one, it becomes V is equal V max with angle of theta, something like that. And then we do all the calculation in complex domain. So do all the calculation complex domain. Then when we are done with all the calculation, transform back result transform results back to uh, sinusoidal form. So as a function of time. So here, basically what we have here is time dependent. We convert this time dependent to phasor, which is not time dependent anymore. And because it's not time dependent, it's much easier to do the calculation on them. So they are not time dependent, but they're complex number. So we use this complex number to do all the calculation in the complex domain. The good thing is that they are not time dependent. The downside is that so they are going to be complex numbers, so it's a little bit more difficult than regular number, but it is still much easier than working with complex number than working with the time dependent values. After we are done and we get to the final result, we convert back all the results to the sinusoidal form, or basically we convert back them from the complex form to the time dependent form. This is and most of them this is how we are going to do a majority of the work that we are going to do here in this chapter. So let's look at the example how we can use the phasor in our calculation. Assume that we have the, for example, the voltage is going to be in form of, for example, 10 cosine omega t plus 5 sine omega t plus 60 and plus 5 cosine omega t plus 90. Assume we have this value and we want to convert it to something like that. We want to add all these three, and eventually we want to come up with something like that. Vt is going to be Vmax cosine omega t plus theta. Assume I want to convert this to this one. So basically I want somehow add these three terms together and find the final result of if I add these three terms together. You know that if I want to do it in the time domain, it's relatively going to be a difficult task to do, if to actually do this trigonometric calculation to find out what's the results of adding these three sinusoidal waves together. But rather doing that, I will come and convert all of them to the phasor first. So I will come here and say that, okay, I have 10 cosine omega t, and then I convert it to the phasor, which is going to be 10 with angle of 0, because it's omega t plus 0 basically. So omega t plus 0, so it's going to be that. Then I have 5 sine omega t plus 60. So first I have to convert them to cosine. So it's going to be 5 sine omega t plus 60 minus 90. So, sorry, so that's going to be cosine. So I convert it to cosine. And now that I converted to cosine, so it's going to, I can say that, so I can convert that. So this is going to be negative 30. So it's going to be 5 with angle of negative 30, because this is going to be negative 30. So I convert that also to phasor. And the third term, so I'm going to write the term. The third term is 5 cosine omega t plus 90. And then I convert it to the phasor, is going to be 5 with angle of 90. So I have these three. So if I put these three together, the VT, now I'm going to write the VT in form of the phasor. So it's going to be 10 with angle of 0 plus 5 with angle of negative 30 plus 5 with angle of 90. So the VT from time domain converted to the VT to the complex domain. Now I have some complex number, and I just need to add these three complex number together, which is much easier to do that. So the VT, the first one, so I'm going to convert these to rectangular form. Remember, let me go back to this one. If you want to add or subtract a complex number, it's easier to have them in this rectangular form. If you want to multiply or divide them, it's easier to have them in this polar format. So when we want to add or subtract, we have to convert them to from here to rectangle. So I have z with angle of theta, and then to convert it to rectangular form is going to be z cosine theta plus jz sine theta. So basically, this is what I have. Because I want to add and subtract a complex number, I convert this to this form here. So I will go ahead and write it here. So the first one is going to be 10 cosine 0 plus j 10 sine 0. Then the second term is going to be this one. The second term is going to be 5 cosine negative 30 plus j 5 sine negative 30. And the third term is going to be 5 cosine 90 plus j, and then sine 90. So let me write them right here. So this part is 10 with angle of 0. This is the second term, which is 5 with the angle of negative 30. And this is the third part, which is going to be 5 with the angle of 90 degrees that we have. So if I go ahead and, for example, we know that, for example, the sine 0 is 0. So this is going to be, and the cosine 0 is 1. So it's going to be just 10, or the same here. If I do the calculation, all of these, and remember that here, look at the 10 angle of 0 or 5 the angle of 90. This is what I was talking about it in earlier. These are what we, so if it's a magnitude with angle of 0, it's going to be just its magnitude, the complex number angle of 0. The complex number with angle of 90 is going to be jz. And so you can either write the whole thing, or if you remember that, you can just simply put the very final magnitude there. Anyway, so if I do this calculation and put all of them together, add them together, eventually what I'm gonna get is gonna be 14.33 plus j 2.5. 2.5. So this is what I'm getting here. So this is in the rectangular format. Now I have to go and convert it back to the polar format. So let me go back again. So what I have here is in this format, the rectangular format, and I want to convert it to polar format using these two equations, basically. to get the polar format of that. So from this to this, using this equation. So again, if I just write it here, I know that if I have a z is x plus jy, then z can be written as a magnitude of the z with angle of theta, and the magnitude of the z is x squared plus y squared, and the theta is tangent inverse of y over x. So therefore here I have the Vt is 14.33 plus J 2.5. Then the magnitude of the V, if I use this equation, it's going to be 14.33 squared plus 2.5 squared, square root of that. And the theta is going to be tangent inverse of y over x. So it's going to be 2.5 over 14.33, which this one and this one is going to be 14.54, and this one is going to be 9.9. So therefore the V is going to be in the polar format is going to be 14.54 with an angle of 9.9. Now that I have this is my final result in the complex number. Now I go ahead and convert it back to Phasor format. So we transform the final result back to the sinusoidal form. So here, now I have it in this form, and I want to convert it to this form. So I have, for example, V is the V max with angle of theta, and I want to write it back like that. So it's going to be V max cosine omega t plus theta. So I would do the same thing here. So I would write it one more time here. So I know that if the V is V max cosine omega t plus theta, then we know back and forth V is V max with angle of theta. So therefore I have the V is here. V is 14.54 with angle of 9.9. Therefore I can convert it back to the time domain as 14.54 cosine omega t plus 9.9. So this is going to be the final. So this is what we were looking at that. So we wanted to know how it's going to be the final value like that. One thing that before I just go ahead is that remember that we can do this because all of them has the same omega. If you look at here, because all of them has the same omega, we can do it. If we have different value for the omega, we cannot use this method. But usually, and throughout this chapter, always we have the same omega. But know that we can do this because the value for the omega is the same in all of the term. If it was not the same, then we could not do any of these calculations. But very quickly again, if we have something in the time domain, just convert all of them to the phasor. Then we do the calculation in the complex domain. Here we want, for example, to add couple of complex numbers, it's easier to have them in the rectangular format. Just add them, and by the time you get it to the complex format, uh, convert it back um, uh, to polar format. And when you have it in polar format, convert it back to time domain. So you will see how it works. By the time that you get comfortable of doing that, you will see that it's much more easier and faster doing it this way rather than do it with sinusoidal wave here. And also one other things before I move ahead, that make sure that your calculator is able to do this calculation. So although you need to know how to do that, but when you're doing the problem, you just simply can put these, and most of the calculator just, you can just put the, in this form, the polar format, you can put the magnitude of 10 with an angle of 0, 5 with angle of negative 30, or 5 with angle of 50, and it automatically gives you this final value, so you can skip all the calculation in between. So if you enter these three in your calculator, this is what you're going to get. And then when you have this, you can simply just write that. So make sure that you know how to use your calculator to enter the complex number in them and do the calculation. Let's look at another example. See how we can work with the phasor. Again, another example, assume I have two voltage as 20 sine, 20 cosine, sorry, 20 cosine omega t plus minus 45 degrees. And then the V2t is 10 sine omega t plus 60. Now assume I have these two, and I want to know what is the Vs if the Vs is the V1t plus V2 V2t. So if I add these two, what's going to be the Vs? Again, if I want to add this cosine and sine wave in the time domain, it's not going to be easy. So the way I'm going to do that is I'm going to convert them to phasor first. Basically, I convert them to complex number, do the calculation complex number, and then convert them back to time domain. So the V1t is 20 cosine omega t minus 45. Then in the phasor, so the V1 is going to be 20 with the angle of negative 45. V2 is 10 sine omega t plus 60. And then we have to convert it to cosine. So it's going to be 10 cosine omega t plus 60. And to convert it to cosine, just subtract 90 out of that, which is going to be here again, it's going to be negative 30. It's going to be negative 30. And now I can convert it to phasor. So the V2 is going to be 10 with angle of negative 30. Now I will do this calculation. So the Vs is going to be V1t plus V2t. So it's going to be 20 with angle 45 plus 10 with angle of negative 30. And if you have your calculator, you can simply plug it in your calculator and do the calculation. But I'm just gonna write the complete solution. Again, these are in polar format. The easiest way to do to add and subtract it. I would say to add and subtract the complex number is to convert them to um, rectangular format. So it's going to be 20 cosine negative 45 plus j 20 sine negative 45. So it's going to be the first term, then plus 10 cosine negative 30 plus j 10 sine negative 30. And so then this one is 20 negative 45, and this one is 10 negative 30. And then if you simply just add all the real part together, add all the complex part together, what we are going to get is going to be 22.8 minus j 19.14. And then if I convert it to polar format, as I said, again, I will just very quickly write it down here. So if I have the z is going to be x plus jy, it can be written as z with angle of theta, and the magnitude of the z is going to be x squared plus y squared, and the theta is going to be tangent inverse of y over x. So therefore I have the vs is 22.8 minus j 19.14, and then it can use this equation, can convert it to polar format, which is going to be 29.77 with angle of negative 40.1. And now that I have it as a polar format, I can go ahead and convert it back to time domain. So Vs as a time is going to be 29.77 cosine omega t minus 40.01. So go from this. Again, as I said, if you have your calculator, after you enter these two, you can enter these two into your calculator, and directly it's going to give you this value here. So you don't need to do any of these calculation in between. So make sure that you know how to use your calculator. Plug this plus this, and then it directly gives you this magnitude, and then you just simply convert it from the phasor back to time domain. So usually you can skip all these middle steps if you have your calculator. Next thing that I want to talk about is that assume we have some very simple. For example, we know that if we have the z is going to be the magnitude of the z with angle of theta, then we can show it in the We can show it in the real and imaginary format like that. So we can come here and say that if this is a real value, this is the imaginary value. We can say that, okay, this is the z. So the z has the magnitude of the z, has the magnitude of the z, angle of theta. This is how we can we show uh, uh, this is how we show these complex numbers. Now, if I come here and convert that to this, so instead of z, I'm going to have, assume I have the z is going to be the magnitude of the z and with angle of omega t plus theta. So instead of having the constant angle, I have an angle as a function of time. So let me go ahead and draw axis again. This time assume, let me bring it over here. So this is my real one, and this is the imaginary part. Now assume I want to show it on this one. So when I have to show this one, because it's going to be the time dependent, I have to start with put the values for this. So if I put t equals 0, what I'm going to get is going to assume this is what I'm going to get. It's going to be at the time 0. So it's going to be, so this is the z, and it's going to be, because it's 0, so it's omega t. So that is the z at time 0. So that is the z at t is equal to 0. Now, if I start to so this is the t at time is 0. Now, if I start to increase the t, so instead of having t is 0, make the t is equal to 1 second or 2 seconds or 3 seconds. So this is going to be increased. So basically, so this is at the t0 is going to be theta. Then if it's going to be 1, it's going to be omega plus theta. If it's going to be 2, it's going to be 2 omega plus theta. If it's going to be 3, it's going to be 3 omega plus theta. The magnitude is not changing, so the length of the vector is not changing. It's always z. But this angle, by increasing the theta, is going to start to increase. So if I let me rewrite this as a so this angle is omega t plus theta. And if the t is 0, so it's going to be at the initial location. If the t start to increase, this angle start to increase. So basically this, because the length is constant, only the angle increases, it starts to rotate. It's like that. Make it a little bit longer. So this starts to rotate as the t increase. So basically this is here, then it comes somewhere here, then it comes somewhere here, then it comes somewhere here, depending on the t. So it starts to rotate as the theta increase. So it's initial location, then it comes, for example, to some location like here, then it comes to some location, some here, then it comes to some locations. Depend on the t. As the t increase, this vector start to rotate. So basically, when we insert the time dependent factor in here, instead of here that we have a constant vector, here we have a rotating vector as the t, because as the t change, the angle change. So keep changing the t, keep changing the angle. So the location of that keep changing is like that it is rotating um, uh, here. Now, if I come here and I know this is the real value part of that, if I come here and say I'm gonna see the projection of that here. So if I come here, say, so this is the real part of that vector, and this is the time. So if this is going to be the time, and this is going to be the real part of that z, so the real part of the z. So I'm going to just project every point from there to this location. So at initial location, when the t is 0, it's there. So it's going to be here. And then as it starts to rotate, for example, it comes at this point. So it's, I know that initially this is the real value. This is the real part. Then when it rotates and comes here, this is going to be the real value. And then when it becomes vertical, the real value becomes 0. Then when it, for example, is here, comes somewhere here, this is going to be the real value, the projection of that real value. If I start to draw those real value, every point that it goes and collect them. So eventually what I'm going to have is going to be something like that. So I'm going to have some form of, for example, sinusoidal wave. If I just plot the real value of that rotating part. So whatever is the projection of that vector on the real value at each time, I draw it here. It's going to be there. So it's going to be this form. Now, look at this. I can write this equation. I know that the z, if it is plus theta, I can write it as a z cosine theta plus j z sine theta. So this is the real part. We know that from the complex number. So this is the real part. Oh, sorry, I forgot the omega t. It has the omega t of it. So it's going to be cosine omega t plus theta plus j z sine omega t plus theta. So this part from the complex number, we know that this is going to be the real value of the z. So it's the real of the z. And we know that this part is going to be the imaginary part of the z. And then it's got the complex number. Now look at this is what I draw here is the real part of the z because I project it here. So the real part of the z is going to be z cosine omega t plus theta. Now look at this z cosine omega t plus theta is very similar to what we have for any for example, case they have. For example, we write the v is the v max cosine omega t plus theta. So look at this and look at this. So basically, this one is the real part of um, um, a complex number. So I can write this as a real part of basically this. So I can write it as a real part of V max with angle of omega t plus theta. Now, what is the phasor for this? So look at this again. If I have V max cosine omega t plus theta, the phasor for that is V max with angle of theta. Compare these two together. Here I have V max with angle of omega t plus theta. Here I have V max with angle of theta. So this part is the same as here if the t is 0. So all of these I want to say that is this on the only this point. The phasor is a snapshot of I would say a snapshot of this rotating complex number at t equal to 0. So basically, when we say that we convert this cosine wave to the complex format, what we do is that we assume we convert it to the complex format, and then we assume the time is 0. We fix the time as 0, and that's all happened. So it's all these is just basically the concepts of why we go from the time domain to the complex domain and vice versa. So it's like that we actually can write this as this full complex format and then only look at the real part of that and then put the time equals 0, because if I set the time equals 0, these terms become 0. This sign, oh no, it's not become 0. So sorry, look at this part and then set the time is 0. So omega t is becomes 0. And then we look at that snapshot at t equals 0, look at the real value of that and do the calculation. So this is basically this is the concept behind how we can go from the sinusoidal wave to the phasor and vice versa. If just conceptually you want to know what's the phasor is a complex number at t is 0. So that's how it is. But the last thing I want to talk about the phasor is the phase relationship. So assume I have two voltage as V1 is equal to 3 cosine omega t plus 40 and the V2 is 4 cosine omega t minus 20. So assume I have um, uh, these two equations. So if I write them as a phasor, so this one, the V1 is going to be 3 with angle of 40. And the second one is going to be the V2 is going to be 4 with angle of negative 20. Now if I go ahead and draw them on the as a vector, draw this on the as a polar vector. So if I go ahead and draw them, so the V1 has a length of 3 and angle of 40. So it's going to be, as for example, this is angle of 40 and length of 3. So I know the length is 3 and the angle is 40. So this is the V1. Now if I draw the V2 has a length of 4 with angle of negative 20. So assume this is the negative 20. And this is 4. Now let me try to see if I can. Oops. So assume this is length is 4 and this angle is negative 20. And look at that, we measure everything basically counterclockwise. And so this is going to be the V2 that we consider. So angle between these two is going to be 60 degrees. So if I come here and this angle between these two from here to here is 60 degrees. Now look at them and consider them counterclockwise. When the one that counterclockwise is ahead of the other one, we call them it's leading. So basically we will say here, here we will say that V1 leads in the format of counterclockwise. So let me probably draw this again. So the format of counterclockwise, this is 60 degrees from here to here. So V1 leads V2 by 60 degrees. It's just convention, remember that. So because V1 counterclockwise is ahead of V2, and how much is ahead is 60 degrees. The same here, we would say that V2 lags V1 by 60 degrees. So this is how we consider one is leading and one is lagging. So let me also put some hang here. So we know this is the 40 degrees here, and this is negative 20 degrees here. So basically this, and remember every time we consider the counterclockwise, and we consider the smaller angle because we can consider also this. Well, we consider the smallest angle, smaller angle between the two vectors. So whoever is ahead counterclockwise format is lead. Whoever is behind in the counterclockwise format, we say it lags behind that. So V1 lead V2 or V2 lags V1.